All right, let's dive into one of the biggest, most mind-bending mysteries in the entire universe. It's a cosmic detective story, really, a puzzle that pits the two great pillars of modern physics, general relativity and quantum mechanics, in a fight to the death. This is the story of the black hole information paradox.
And to really get our heads around this, let's start with a pretty simple question. Let's say you had a secret, some piece of information you wanted gone, really gone, from the universe forever. Could you just chuck it into a black hole? Well, the answer to that question is the key to this whole cosmic mystery.
So could you do it? For a long time, the answer seemed to be a resounding yes. Our story begins at the scene of the crime, if you will, the black hole itself, as described by Albert Einstein's theory of general relativity.
Yeah, this is the classic line, right? The one we've all heard. According to general relativity, a black hole is the ultimate one-way street. It's a perfect vault, a cosmic prison from which there is absolutely no escape. Once you're in, you are in for good. So how does this actually work? Well, Einstein's theory tells us that really massive objects literally bend and warp the fabric of space-time around them. A black hole takes this to an insane extreme. It creates this boundary, the event horizon, which is the ultimate point of no return. Cross that line, and you're locked away forever.
This is a fantastic way to picture what's happening. Imagine space-time is a river. Far away from the waterfall, that's our black hole, you're in a boat and you can motor around no problem. But as you get closer to the edge, the current gets stronger and stronger. Right at the edge, which is our event horizon, the water itself is flowing over the falls at maximum speed. Once your boat tips over that edge, there's no engine in the universe powerful enough to fight that current. You're going down.
Okay, so according to Einstein and general relativity, the case is closed. Your secret gets tossed in, and it's gone forever. But here's where our mystery really heats up. Because another theory, one that's just as successful, tells a completely different story.
On one side of the ring, you've got general relativity, the undisputed champion of the big stuff. Planets, stars, galaxies. It says your secret is toast. But in the other corner, you have quantum mechanics, the rule book for the tiny world of atoms and particles. And it has one unbreakable rule. Information can never be destroyed. These two theories have been tested a million times and have never failed until they meet at the edge of a black hole. One of them has to give. At the very heart of quantum mechanics is this ironclad law called unitarity. You can think of it like this. Just like energy can't be created or destroyed, only changed from one form to another, the same goes for information. If you burn a book, for example, the information in it isn't truly gone. It's just been scrambled and rearranged into the smoke, the ash, the heat. It's messy, but it's all still there. Quantum mechanics says this is a fundamental, non-negotiable law of the cosmos.
So we've got this epic showdown, an unbreakable paradox. And just when it seemed like a total stalemate, a shocking new piece of evidence blew the case wide open. In the 1970s, thanks to the legendary Stephen Hawking, he found a loophole.
Hawking came along and asked this absolutely game-changing question. He said, wait a minute, what if these ultimate prisons aren't actually permanent? What if, over enough time, they could just disappear? And this idea changed absolutely everything.
You see, by applying the weird rules of quantum mechanics right to the edge of a black hole, Hawking discovered something incredible. They aren't perfectly black after all. They actually glow, just a tiny, tiny bit, leaking particles and energy back out into space. We call this Hawking radiation. And it means that over unimaginable timescales, trillions and trillions of years, a black hole will slowly shrink and eventually evaporate into nothing.
This is a cool way to think about how this works. The vacuum of space isn't truly empty. It's constantly fizzing with pairs of virtual particles that pop into existence for a split second before vanishing again. Let's call them quantum coins. Now, if a pair of these coins pops up right on the event horizon, it's possible for one to fall into the black hole while its partner escapes. That escaped coin is Hawking radiation. It zips away carrying a tiny speck of the black hole's energy with it.
And this is where the paradox comes back with a vengeance. So the black hole eventually evaporates completely, right? That means the coin that fell inside is gone too. But what about the information that described that coin? Its escaped partner is entangled with it, but the original is gone. It really looks like the information has just been, poof, deleted from the universe. And that violates the most sacred law of quantum mechanics.
Now you have to understand, this wasn't just some dry academic problem. This mind-bending puzzle sparked a fierce, decades-long intellectual war among some of the greatest scientific minds on the planet. Back in '75, Hawking was actually convinced that he'd broken quantum mechanics, that information really was lost. But other physicists, like John Preskill, pushed back hard, insisting that the quantum rules were unbreakable. The whole debate famously led to a public bet in 1997 between them.
And you gotta love the terms of the bet itself. It was just perfect. The prize was an encyclopedia, a book chosen specifically because it was something, quote, from which information can be retrieved at will. So witty. And yeah, in 2004, Hawking famously threw in the towel. He stood up at a conference, admitted he was wrong, and announced that information must somehow get out. He later paid up with a baseball encyclopedia for Preskill.
Okay, so Hawking conceded. Information does get out. But how? I mean, how on earth does it pull off the greatest escape act in the universe? Well, this is where the proposed solutions get truly bizarre. I mean, just look at some of these ideas. You've got the fuzzball theory, which says a black hole isn't a point, but a tangled, stringy ball that holds information on its surface. Others think there are small corrections in the Hawking radiation, that it isn't perfectly random and it slowly leaks the information out in a hidden code. Then you get the really wild stuff, like a deadly firewall of energy at the event horizon, or the idea that the information escapes into a whole new baby universe.
So after all that, where are we now? Well, the dust has settled a bit, and thanks to some huge breakthroughs in just the last few years, the consensus has really shifted. Most physicists are now pretty confident that Hawking was right to concede. Information does escape, quantum mechanics wins the fight. But, and this is a massive but, the information doesn't just come out clean and readable. It comes out shredded, mangled, and completely scrambled into the seemingly random fizz of Hawking radiation. It's like trying to reconstruct that burnt book by analyzing the exact position of every single particle of smoke and ash. In theory, it's all there. In practice, it's impossible. To try and decode the information from a black hole, just the mass of our sun, you'd have to sort through the number of possible combinations you see on the screen right here. That's a 2, followed by, well, a number of zeros so vast you couldn't even write them all down if you used every atom in the universe. It's just mind-bogglingly huge. So yeah, good luck with that. So we have an answer, right? Information is preserved, but it's hopelessly scrambled. Case closed? Nope, not even close. If anything, solving this part of the puzzle has just revealed how much deeper the mystery really goes.
We're still left with these huge, profound questions. We don't know the exact physical mechanism that does the scrambling and gets the information out. We have no real idea what an astronaut falling in would actually experience. Would they see a firewall, a fuzzball? And maybe, most importantly, we don't know how gravity and quantum entanglement really talk to each other to pull off this magic trick.
So in the end, your secret isn't destroyed forever. It does get back out eventually, but in a form so scrambled that for all practical purposes, it might as well be gone. The real takeaway here is this. The quest to understand exactly how this process works is one of the driving forces in physics today. It's a clue that could lead us to a theory of everything, a theory that finally unites gravity and quantum mechanics. Solving this paradox won't just tell us about black holes, it could tell us about the very fabric of reality itself.